Welcome back. Now we'll switch gears, but not completely. So we'll now have Professor Gino Isidori, who will be slowly taking us towards calculations in chiral perturbation theory beyond the leading order. So he'll have several examples which will be worked out of probably photons also at some point, hopefully, and chiral Lagrangians. So Gino.
Okay, so it's really is a big pleasure to be here. And so maybe, yeah, as the other speaker said, so maybe I should say something about me. Okay, my name, you've seen it. And so you if you want to write me very simple email address, so I'm in Zurich, and actually I worked when I was young. Indeed, I got my position very early in Frascati laboratory, which was in Italy, where the Pi factory was built, which was basically the Kaon factory. This is why really for the first 15 years, I worked a lot on chiral perturbation theory, given that we had this facility in Frascati. It was really very nice to explore the property of kaons, and therefore chiral perturbation theory was the right tool. Now, then I moved, now I'm in Zurich. Actually, in the second 15 years, I've been working more on BSM physics, and a lot of bit of model building, and still with a special eye on flavor physics. And I think chiral perturbation theory, I'm not really recently too much working on it, but on the other hand, I still think it's a very, very natural and useful tool for effective theory in general, also for model building. For instance, composite physics, probably Professor Kaplan later on tomorrow will discuss more about composite physics, which indeed it's a variation of chiral perturbation theory, but on a different system. Okay. So actually, this lecture, I have the title is chiral perturbation theory beyond lowest order. Maybe a better title would be more about I'll try to discuss it in relatively general terms, and also I will try to get. I was wondering how should I start. I mean, given you already had an introduction on the subject, so I'll try to take a bit of an orthogonal view on the subject, maybe a bit more formal. So I do the European way. You have the beautiful, intuitive, and which is very, very nice way to look at the problem. So I took more the European way, which is a bit more formal, but which is useful to go on the technical level. Indeed, also historically, I think chiral perturbation theory was basically the seeds were all set by Weinberg in this famous paper in the 70s about the Pion scattering length. But then a big breakthrough happened in the mid-80s with Gassner and Lloyd-Wheeler, who really showed the full power of taking this as a complete quantum field theory, renormalizing it, and computing order by order. And this can be done in a systematic way. So, yeah, as a start, maybe I was thinking it's also good to set a few basic things about KPT, also in general about effective theories. So, as you've seen also in the previous lecture, to define well an effective theory, I think really three important ingredients need to be defined, which are, there are three basic ingredients. Any quantum effective field theory. So these are the degrees of freedom, the symmetries, and the power counting. Really, to define an EFT, you have to specify these ingredients. So these are really the basic building blocks of any quantum effective field theory. So let's look at how we do in what we'll call the basic IPT. So in terms of degrees of freedom, I want to do this in comparison with possible variation, okay? By the way, please ask me question anytime, okay? I see you are a bit too shy. So, okay, now you don't need to ask questions, but okay, whenever you want, please ask question. I say this not to forget. No problem to interrupt. So in terms of degrees of freedom, as you see, the basic ingredient of chiral perturbation theory is to build a theory where the degrees of freedom are the Goldstone boson or the pseudo Goldstone boson of this broken symmetry. So we, depending on, we have these, so are the pseudo Goldstone boson, Nambu Goldstone boson, as some people say, of QCD, that depending if you go to an F equal 2 or an F equal 3, as you've already seen, these are the pions or the pions plus the kaons and the, okay. A natural possible variation that we'll discuss later on is, for instance, to add the photon as dynamical field. I'm stressing this, which is a separate story, because of course we can discuss the photons as an external source in chiral perturbation theory, so something that, okay, coupled to the photon, but then we don't look at really loops with photons and pions. If we want to have loop with photon and pions, if we want to treat the photon as dynamical field, which of course makes sense because the photon mass, it's zero, so clearly it's always there, then we have to build a different theory, okay? So it really will be a different EFT with different degrees of freedom. This is why it's important to stress it. On the other hand, of course, in this basic theory, we can discuss the interaction of these Nambu-Goldstone boson with any external field, for instance, as you've seen before with the W, okay, or again with an external photons, because this is something that we treat externally, I mean non-dynamically from the point of view of our FT. The symmetries. Symmetries, as you see, the key assumption is this assumption left part item is the SU2, the SUN vectorial subgroup. So depending what NF is, we have seen there are this option. So this is really the key assumption. And when we discuss symmetry, we also need to discuss at the same time, also it's very important, the symmetry breaking. And the minimal things that we cannot proceed without is to describe the quark masses. Okay. And we discuss quark masses as spurions, that is, as something that has a well-defined transformation under the symmetry, but break it explicitly in a well-defined way. And actually, this, we'll discuss it also in more general terms, we allow us to discuss all possible effects related to the quark masses. And again, I'm stressing this because then we can add other spurions. For instance, we can add maybe related to weak interaction, or even related to DSM physics. And also as a symmetry, this is a global. Okay. We can also discuss together with adding the photon, adding as a local. Local UN. So these are all extension of our basic construction. Okay, sorry, I like to be a bit systematic. This is why you give all these things. And I want to stress this is because it's relevant also when you want to build your own EFT, which I really encourage you to do. Of course, it's important to discuss also when we discuss physics beyond the standard model of symmetry, and symmetry breaking is very important. So the symmetry breaking, there is a well-defined way to treat the symmetry breaking in a systematic way if the symmetry breaking is small in FT, which is this spurion technique. And finally, here, I don't have the space to write the power counting, but maybe is the okay, maybe this I put it here because now we understood what this means. Power counting here, this will be an expansion in the momenta of our custom bosons divided by a scale lambda, okay, that we will identify is related to QCD. Actually, it's not really lambda QCD, fortunately, otherwise the radius will be very small, will be more related to the raw mass or even more the proton mass or something around 1 GeV. And we will see, I mean, there is a consistency of the theory that tell us somehow what this scale is. And again, we have to, if we want to extend the theory, for instance, when we want to have photon as dynamical field, we also need to have an expansion in alpha, which is a different expansion. So then the combination of the expansion in these two things, okay, it's non-trivial. So certain things maybe you can do resummation in alpha at fixed order in the carrier expansion or vice versa. And again, the interplay of the two expansions is non-trivial. And again, this is really, I'm stressing that these are different. In each case, you need a different Lagrange, okay, if you want to discuss these other things. Okay, so that was really the basic setup. So let's start with our basic KPT. And the way I want to introduce it, again, being a bit orthogonal to what was done before, is to really start from this assumption that indeed we have this pseudo-Gaussian boson. I want to keep it general, so we can take carrier perturbation theory as a prototype of theories where our degrees of freedom are the Gaussian boson of a global symmetry G broken into a subgroup H. So that is the goal of the formula that I want to introduce, which is called the Callan-Coleman-West-Zumino formalism. So Callan-Coleman-West-Zumino really asks this question. So if we have a system where we know that there is a global symmetry G broken into A. So this is the symmetry of the ground state. As you know, in this case, we know that that we will have a Gaussian boson. Okay, Gaussian theory tell that we have Ng minus Nh, that we call it an A broken generator. And these broken generators are in one-to-one with Goldstone. The Gaussian bosons are really the excitation associated to the number of broken generators. So now we want to build a theory. This is a bit special because we are used to the fact that we have the field, that we have the symmetry. So we define how the field transforms under the symmetry. Okay? Here, our variables are the Gaussian bosons, which are somehow element of the symmetry for which we want to build the theory. So this is a bit peculiar. Okay? So we really want to build a theory where the element of the theory are part of the group that describe the symmetry of the theory. So how to do that? Again, this is a bit formal, but I think it's useful. This is why I want to discuss it. So suppose we have any element of the group G. This we can decompose it as generically as something like this. So for me, AI are the broken generators, while the unbroken generator are the VI. Okay? So an element of the group can always unambiguously decompose it as a series of rotation along the broken generation and a series of rotation along the unbroken generator, right? Just decomposing by group. Now, so this is, again, this is the transformation property. If the transformation is global, this will be global parameters. Now, what are the Gaussian bosons? The Gaussian bosons are, if you want, the idea of transforming this parameter as local x-dependent quantities. Okay, so now I want to understand if I promote this to be a field-dependent or what a space-time dependent quantity, the element of my group, of my global symmetry, I want to understand how this transforms. Okay. And so okay, this is just a definition. Now, suppose I take indeed a generic element, so a generic object like this, okay? So this is indeed, it's an element of the group, which however now I make it local on the broken generator. Now, if I add with now an element of the group on this other element, because of this general decomposition, this will be written, has to be written as like this. Because this is also an element of the group, right? But now, because of this x-dependence now propagate both on the unbroken and the broken, sorry, the broken and the unbroken generator. Now, what Carla and Colin and Zumino demonstrated is actually this transformation provide not only this transformation together with the, sorry, I should tell you how does elements transform under, suppose that now we have something, I take an object, a field psi that under the unbroken group transform in a well-defined way. So this is a linear transformation, okay? Under, this is a generic representation, this I write it with this T, okay? So for me, H is an element of this group here. Now, this combination so the change of the Gosson-Boson variable together with the transformation of the field with the well-defined transformation property under H under this transformed value, this provides the most general representation of the group in terms of the transformation property of the Gosson-Boson, which also has the property to reduce to a linear representation when we restrict our attention to transformation that belong only to the unbroken subgroup. Again, this is all a bit formal. So let me first prove that, which is very simple if you know a little bit of group theory. And then let's look at more specifically what this implies for our system. Yep. Yeah, generically they don't commute. So generically they don't commute. But however, I can always find this form, okay? I can always rearrange in such a way. So of course it's different. So this is different. So these two do not commute generically, okay? But on the other hand, I can always write it. I can always find this type of decomposition. This is general. Yeah, yes. Yes, then I can do, but then we'll complicate the situation. This is the most convenient decomposition, which is what I need to prove, okay, this fact. So this combination where you first act with the unbroken generator and then with the broken one is the most convenient, because then I want to read it. I want to see, because I want to act with my group element on this, which is really the Gosson-Boson coordinate. Okay, so I'm really interested in what happens to this object here. Okay. Okay. Yes? D as a generic representation, for instance, example. Psi is in the fundamental, then I would say this will go like this, or psi is in the adjoint, then will go as like, and so on. Okay. All of these I write them like this. Okay, thanks for the question. So, yeah, let's prove that this is indeed a representation of the group, which is not obvious. How to do that? Well, if it is a representation of the group, it means that if the say I go from G1, or we call it G0. So sorry, G0 brings me from psi to psi prime, which means that G0 e to the psi A is equal to e to the. Now I forgot I don't write anymore the X, okay, but now remember all this depends on X. Okay, sorry. Okay, and then if G1 brings you from, then I should show that then I need to show that G1, G0 applied on X, this will be again an element of the group, will bring you to psi 2. Okay, that is what I need to show. So here, let me call it. So these are their definition. This is what I need to prove, and also I need to prove the same thing also for the D part. And so let's see how. Let me act on take the note just to see how I do it, not to scrap. Yeah. Oh, this because so if I act with this element and arrive here, and then I act with this element from here to here, then if I act on the combination, so this is the order matter. So if I act on this, which will be a new element, okay, but is a well-defined order. So first G0 and then G1, then I want to start from here and arrive to there, okay? Which again is not completely obvious because, see, let's see what happens when I act on G1 on. So I know how G1 acts on these things here, okay? This is by definition. Let's now, but I want to see how G1 act, okay, on G0 e to the. That is now what I want to see, okay? Now this is G1 acting on e to the. Okay. Now this again will be a new element of the group. So I will call it, since this is again an element of the group, I can always find this form, okay? So let's write it here. So this will be e to the xi, let me call it 3, a e to the eta 3, 3. Now you see, from that point of view, again, it's trivial. The fact that what this then is the yeah. On the other hand, okay, this is true. On the other hand, now I can decompose that. I act first on this, and then I have this term here. So I will have this expression here. Yeah. And then I have. Okay, so this is when I acted first on this, and then I have. So this is happening when I act with G1 on this term here. So you see that again, it's a very simple thing. What I find that these two terms have to be identical because now these two commute because they are part of the same group. So this has to be equal to. Okay? So this has to be an element of V, and therefore this term has to be identical to this one. So actually this term, okay, is identical to this term. So I prove that this is that, which is exactly what I wanted to show. Okay? And finally, you see also here that the composition, so now when I will act with this element here, I will basically have the product, okay, of the two terms which I got with acting separately on the two groups. Okay. Yes. They are whatever they are, but they have to be an element of the group. The point that this decomposition is unique. Sure, absolutely, you're right, sorry. They don't commute general, but they belong to the same group. So you'll never get an A here. This is the point. Sorry, thanks a lot for a clarification. So this is an element of V, and therefore it has to be this element here. Right, thank you. Finally, and also what is interesting to discuss is that is the linearity and non-linearity of all these. Okay. See, this transformation is in general non-linear. That is, this psi prime of x will depend on x, but also will depend on the xi in a non-trivial way. Okay? Well, you see, this is what I call linear transformation. So here, my transformation, so this was adjoint. These are all linear transformations that do not depend, indeed, they do not depend on the value of the field. Okay? So if you want, the dependence on the value of the field is linear. While in this other case, the dependence is non-linear. On the other hand, this reduced to a linear dependence when we restrict to the vector, to the unbroken subgroup. So so indeed, what happens when I act? Now this is the element of H. Okay, so this will be whatever. Okay, actually this I want will be something like this, but now I can write it as let's assume that the group is a unitary group. And so now this, again, because of the uniqueness of the group, this will be the uniqueness of the composition, while this is my. So this now becomes a linear transformation. So when I restrict to H, okay, again, given the fact that here I could put H dagger H because, and then this is an e to the EV, again, because of the uniqueness of the composition, this has to be an element of the group, the broken one, sorry, which is not a group, okay? And this is why my transformation of is like this, which is, if you want, is the complicated way to show you what Professor Kaplan showed you before, in a nice way of the fact that the pion was transforming as a fundamental of the SU3 vectorial. That's exactly, so this is my pion field and it goes like this. Okay. Got the two sides of the two way to see the things, the bit more formal where the, okay, good. So, okay, now I'm almost done with the more formal math part. So finally, now let's try to connect to physics and to finally see what this element is. Well, maybe, okay, sorry, so still there is a slight technical step which I need to make. So you see clearly this element e to the xi A, it's our basic building block. And sorry, let's rewrite that equation there. So now this, I will call it little u, okay? And this will be my u prime. So this how this little u transform. And this element, okay, this is an element of my group H, okay? But now this eta prime for generic transformation, it's a nonlinear representation, so I call it H of x to remember that this is nonlinear, okay? because it depends on where I started with my coordinate xi. So I start in a generic position of the group in any different points in space, then I do this rotation, so clearly my element depends. So what I see here is that now let's multiply by g minus 1, so I get that the transformation property of this field is this one. I'm simply inverting with respect to u prime. Okay, so u prime is equal to g, u, and then I multiply by h dagger and I get that. So this little u, I call it is a compensator field, because what it does, I mean, it's something that you see as a transform in a mixed form under the full group G, and on the right side on the unbroken group, but with a nonlinear dependence on the Gaussian-Boson coordinate. So this is very powerful because, for instance, if I have my field in the fundamental, okay, so for instance, my row meson, and I want to construct something that has some object from the field point of view that has well transformation property not only under SU3 vectorial, but as transformation property, well-defined transformation property under the big G, then I can do that combining with this little u. So for instance, if psi transform into, now, for instance, this I deduce it because I look at my spectrum, I see that, and also my property, I look at my row meson, the case that they form an octet. So the octet then would be something like this, okay? While my baryon would have been a fundamental. But suppose now I have an octet, and then I want to build something that transforms on the other hand with the well-defined transformation property under G. What I can do, I can, for instance, sandwich this with U, and I do U psi. And this will transform as G. Okay. And that's exactly, again, this is the fancy way to show what was discussed before, that basically here psi is my well-defined transformation property, my multiplet under the vectorial group. Then if I combine it with this arbitrary number of pions, which are sitting inside U, then I get something that transforms and can use it to build something which has well-defined transformation property under the original symmetry of the Lagrangian. Okay, so this is why this field is very useful. Finally, to finally match back to what Professor Kappel showed you before. Now we have to specify, this is completely general. For instance, you can use it if you want to build your composite X model, specify what is G, what is A. And finally, this U, see here is a combination of your Gaussian-Boson variable and the broken generator. So you need to know which are the broken generator. Now in the case of QCD, we have this nice extra property that, so G is SUN. Which enjoys an extra symmetry and an automorphism which is parity. Okay, and this is because this is broken into and parity, what it does, parity is the exchange left to right. Okay, so under parity, G goes into G, H goes into H. In terms of generators, the unbroken generator, while the broken generator, not by chance we call act because they are the axial one, goes into minus A. Okay? So this gives an extra property that we will see to understand better it's an extra property on this U field which allows us to build more useful quantities, okay? Specifically for the case where we have this structure here. Suppose, see, this is general. Now I really want to define my U in the case of QCD such that get that transformation property when G belongs to SU2 right. So suppose I define U okay. Again, remember, U is something that depends, is just an exponential of my broken genus. So if I act with parity, what I get U dagger and this will be G right become G left. Right, just because of parity. And so this is nice because now on the other hand, here if I take Hermitian conjugate, I get that U of X transform into, now I really take the Hermitian conjugate of this, and I get sorry, this becomes H. Okay, so finally this has to be equal to that. And similar, so we get this nice thing that this is equal to H. This was dagger. Dagger. And okay. Now this from the conjugate, from the conjugate of this one here, I get okay. So this is a you have this special extra relation coming from in this specific case, which finally, okay, allow us to build. Now I can take, for instance, you know, if I take the product of U of X times U of X, which I call big U, just U square, okay. This will transform into G, right? U of X. Here I take H dagger, but then I put this other expression here, which I can use whatever I want. So I will get, right? So while U dagger will transform into G left, right dagger. And now the most important equation of this lecture is that, so my U dagger is equal to of the sigma to the previous lecture, okay? Sorry for the bad notation. This is it is a big US European discussion which dates 20 years, so I'm not going to change it, but joke, but okay, I hope you get the point. You read what something that was transforming as, and okay, previous was called left and right, it's exactly my U dagger, which is the square, okay, this is the square of this compensator field. And in this way, because actually the compensator field, we will need it somewhere, especially in the future for more complicated construction. So it's good to have to introduce this object here. In the case of QCD or any theory enjoying these automorphisms, the square becomes something that transforms completely linear under the group, which is in a sense nice. See, these things do not depend on X if I'm doing global transformation. While on the other hand, these H depend on X. Okay, so this is very important. And also, again, it's important when you want to build when you want to see how your pion interact with something for which you know the transformation property under SU3 vectorial, okay? There you really need to use this compensator field. Otherwise, you don't know how to do it. Okay. So again, just to close the thing, so for instance, we can even build a covariant derivative with respect to derivative acting on this H, which can be useful. So for instance, again, if I have my usual example there of my field psi that transform into this generically, when I so on the transformation, generic transformation of G will transform in this way, which will this object depending on H. Therefore, I need to put in something if I want to build a covariant derivative, okay? So I can write it. And this. Which actually this is anti-Hermitian, okay, this object here. So this is a little exercise for you to get familiar with this. Prove that this d mu psi transform as psi. Okay. Because again, because these things, when the normal derivative will act here, will have non-trivial effect, which are compensated by this compensator field with the corresponding derivative. Okay. Okay, so yeah, basically this is all the formal things, which is good. Let me see what I want to discuss. Sorry. Yeah. Yeah. Sorry. Yes, again, because also I implicitly assume that all my group are unitary. Okay. Yeah. So H to the -1 is equal to H dagger. Yeah. That was also an implicit assumption which I made. Because basically, so what I didn't told you that indeed if U is my is, so I told you that under parity A goes to minus A. So that is what I'm implicitly assuming. Okay, and this is a unit, so there is a high hidden there which I don't not even written. Okay, so that is what I use. Okay. Okay, thanks again for questions. Are there more questions on this part here? Okay, finally, we want to see a pion. I understand it's time. So let's go back here. So clearly, so we have this U of X that we discussed is the, and for that we have to find a, so this is an element of the group. Okay, now you understood this is an element of the group, but now we want to, this psi of X are these coordinates, which are numbers, are function, okay, depending on X, and we want to promote to be a field. And this is why this that will be, okay, now written it a bit more. Now here we'll have a 2, okay. I have to do a sum, and this is what, again, you have seen it, this is the sigma matrix that was introduced before. So here I introduce a scale, okay. This will be, for instance, in the case of, there can be this will be the Pauli matrices or the Galois generator, depending on if we have n equals 2 or n equals 3. And so this is, finally, I will write it as with some, normalization like this, where this f is just the sum of this x times the corresponding generator, which is exactly the things we have seen before. I put only a square root of 2 instead of a 2 because I like to have the phi, okay. For me, it will be this matrix. I give it directly the bk0. Oh, this is, and if you put the eta here, it will be minus eta over square root of 6 minus eta over square root of 6. And here there is, sorry, this is the minus. This is 0, and here we have 2 eta. Okay. Over square root of 6, maybe 4. Okay, anyway, the usual stuff. Okay, and okay, so this is exactly, so instead of having the 1 over square root of 2, I put it there, so instead of the 2, but this is exactly the same thing you've seen before, and again, my f is the same they've seen before, so f is equal to f, okay, which is this constant which appeared there. We somehow give you, so this f is what tells you somehow how these dimensional field, the piods, okay, are connected to this adimensional variable, okay, which is now, this is a formal body thing. You have seen before how we can determine this f from the decay constant of the pion. Okay. Again, in the spirit of looking at it from a different way, how to determine f, I think, again, a more formal but I think useful approach is the following. We can, so now we will write Lagrangian in terms of these u or sigma, okay, and derivative. But I think it's nice if we really want to match with QCD to look at the full generating functional, okay? So, we can define the generating functional of QCD with some external field. So for instance, I can define L, R, and some scalar field. What I mean by that? I mean the integral of work. So this object, I know. So here there is the QCD Lagrangian in the chiral limit. Okay. So for a moment, forget about the heavy quark integrated out. I only restrict to the attention to the light quarks. So this will depend on my work and gluon, but no masses. Okay. It's the QCD Lagrangian in the chiral limit. Then I want to add here some external field. So to build the generating functional, you know what the generating functional is. So we couple to our dynamical field some source. So let me save space. Okay. So for instance, I can write something like this. This will be, I can bring it out, but I put it here in this form. This is flavor, okay? I is flavor, that goes from 1 to 2 or 1 to 3. This L is one of my external sources, and so it coupled to a quark left-handed current. And then I can write something similar for the right-handed current. And also something for the scalar current. And here, this is non-Hermitian, so I put also the Hermitian conjugate. Okay. So you see, Okay, so this is my generative function that depend on L, R, and S. And I want to integrate everything about. The idea is that, really the idea, what we really want to do is to really do a theory of QCD. So the idea is to rewrite this, but now in terms of my U field, okay? And here I will have my Lagrangian, okay, of my Chiral Lagrangian. That will depend on this, but also on the external field. Now, the power of this, the powerness of this method is that finally, when I look at the derivative of the generative function with respect to external sources, this becomes expectation value of certain quark operator. So for instance, here, it's clear that if I do the derivative of the generative function with respect to L, okay, this, and then I set all the other, let me also generically call them this equal to 0, this will give me the expectation value on the ground state of what? Of the current associated to L. So if I do here Ij, I will get Q bar left, mu Q left, Ij. Strictly speaking, this is on the vacuum, but actually pions do not count because they are also vacuum, okay? So basically, if I do this, I get this object here, and I don't know how to compute that, okay? But on the other hand, I can compute that with my Lagrangian when I put in, okay? I couple my U field to my external field, and then I will get an equation, a relation between matrix element at the QCD level, which maybe I can measure. For instance, in this case of the pion degree constant, I can measure this, but in the other case, I can measure it on the lattice, and then something which, on the other hand, depends on the low energy constant of my theory, okay, which connect to the coupling to my to the pions, to the U, to my external field. And here the power comes that I cannot, I mean, since this L and S, from the way they are coupled to quarks, okay, they have well-defined transformation property, okay? They are defined to objects which have well-defined transformation property under G, and therefore this implies that their coupling to U is completely determined by the symmetries. And this is allow me to do that, to really construct this. So let's see that for the how much time do I have? Okay, let's start just with the actually, you already seen the case of the mass, the quark masses, right? So the quark masses, you have seen it in the previous lecture. Basically, this can be, not only we can compute certain matrix element, but we can also describe specific breaking terms. For instance, let me just discuss how we couple to the external field, to the vector field, which is easy. So our lowest order, so this Lagrangian, this guy, we will write it in a sum of where n now stands for the number of derivative, which is connected to the power counting that, okay, we'll discuss it next time. The lowest order Lagrangian, okay, you have already seen it, is just this. The lowest order Lagrangian without external sources is just this. This stands for trace. Okay, this symbol here maybe. Because it's clear that this is invariant, right? Given the transformation property that we've seen. Again, you see, maybe 1 second more. The fact that you transform linearly under the group, we have it somewhere there, it tells us that here the normal derivative is fine because this is a global transformation property. Okay. Now, however, not if we add, so these things L, I mean, the way it's coupled, I can, if I say that L mu transform into GL, if I assign the transformation property to the external source, this term will be invariant under the global transformation property, right? Because this has transformation property. The external field is whatever, but so it's my freedom to decide the transformation property I want to assign, the formal transformation property, because this is external, it's non-dynamical. So with this transformation property, compensate the transformation property of these two fields, and I'm done. However, for vectorial field, I can do even more. I can promote G to be a global symmetry, sorry, a local symmetry. Let me do it here with the right sign. So if I also add now I'm pretending that G also has an X dependence. In this way, I would promote the global symmetry here to become a local symmetry, the part on the left-hand group. And so this would be respected at UC level, and this tells me that I can do it the same way. In a sense, I can, if I impose the local symmetry at the at the Chiral Lagrangian level, this tells me how I couple U to my L mu, which is via a covariant derivative. So again, so the answer is that this, if I want to see how it coupled with the generic, not only U, but also L and R, it's via a covariant derivative. Because this way I recover a local invariance under my group G, and this covariant derivative just the Hermitian conjugate here. Okay, so basically, if I use this covariant derivative, you see clearly now the appearance here of R and L will compensate the transformation property, which are this one here. Okay. You see that with this, I will have formal local invariance. Again, this is all formal because then I don't put a dynamical, a kinetic term for my external sources, okay? But formally, I have a local invariance. So since I had this formal local invariance here, I want to have it also here. So this is how my Lagrangian, how my external field have to appear here. Okay? There is no option. Actually, in this case, there is no free parameter. It's the special virtue of the of the vector field. In the case of the scalar field, there will be a new parameter appearing, okay? Which is the normalization to the is the parameter that connects the quark masses to the meson masses, an overall coupling. But you see that from that, just to finish the exercise. So here I can do what I promised. So now I can take the derivative with respect to L, but now I do it here, okay? And then I will equate to that. And at the lowest order, I simply have to do the derivative here. So L appear in this term here, so I mean nothing that F square over 4. When the L appear, sorry, here, I will have some minus IU mu daga, and then when it appear there, it's the same, so it will be, sorry, I think it will be, I think I did it like, sorry, the L appear here, so I should multiply d mu daga, then U ij the factor of 2, which give me that, okay? Again, check it. And so finally, you see that this term here, okay, has to be equal to that term there. Again, now this we know how to do because actually this is the things we have seen before with the sigma. Then I expand it from this term here. If I expand it to lowest order, you see this needs at least to have a pion because there is a derivative. So if I take the identity in derivative, I don't get 0. So here there is something which is I square root of 2 f and f goes away. So I have something which is linear in f in d mu phi, okay, plus. So something, this is, sorry, here there is the pion. And so I get the derivative of the pion, after the pion, this giving my square root of 2 f mu, which you have seen before. So this f, okay, this f, it's related to this vacuum expectation value, okay? And so this formula is nice because really we can, and we will see when we look at this, will be related really to the vacuum expectation value of q bar left to right on the vacuum. So with these formulas, we can do this, and actually this is a systematic way. So we really see the analogy of Green function or matrix element in QCD and in our theory. Okay, so I think I will stop here. Yep.
In the covariant derivative, is why the relative sign between the R mu and L mu term? The covariant derivative d mu. So the relative sign between R mu and L mu, does that mean like I'll get a?
You mean the order? The order is well fixed because of that. Okay. So you
Not the order, but the sign.
The sign. Yeah, because of the dagger. Okay. So the dagger, when I get the derivative, in one case I get the minus sign.
Okay.
Now
So,
on this overall sign, I don't know, I guess, but I hope this is correct. But for sure there is a relative sign between these two because when I go the derivative here, I get a plus, and here I get a minus with respect. And the transformation property, you see, I fix it, and for R, I fix it also the same way. Sorry, I went a bit fast. So up to changing the sign here, so when you give the same sign on the derivative, you see this is fixed, then clearly here it will appear with different sign because in one case you have G. And note that this term you can always write it, for instance, this term, since G right is equal to 1, this is also equal to minus I d mu G right. Right? So if the derivative act on G right dagger on G right, be different.
and is it because of this? If I expand the U,
Yeah.
take the first term, like because U is e to the power xi, and if take the first term 1, like then it always comes as R mu minus L mu. So it always comes as an axial vector, and not the vector. Is it?
No, but here, okay, if I can do just the derivative and I set all the other to 0. So for instance, in this case, I was just interested to the coupling to L mu. Well, strictly speaking, if you set all the other to 0, then here you will have a normal derivative, okay? So if I do like this, and then I set, so the derivative, sorry, this was, sorry, I did it, but this was, you're right, I did confusion. So I differentiate with respect to L, and then I set all the other j to 0. So then there is no more covariant derivative here. I just need to pick the terms which are linear in L, okay? And there is, this is what. Yeah. Of course, you can also differentiate with respect to L minus R or L plus R. You can do whatever you want.
Different basis, like.
No, then you get different currents. So you get the vector current, the axial current.
Yeah.
So in this case, of course, this is a piece. When you get L, you get both vector and axial. Indeed, if you expand this term, you get a term with 1 pions, also a term with 2 pions. The term of 2 pions is of the vector current. The term of 1 pion is of the axial current. if you do the derivative with respect to L minus R, so you pick up only the axial current, then you will see that you have only odd powers. So the mu phi then I turn with 3 pions and so on. While if you do L plus R, which is the vector, then you get start with 2 pions. This is a very good exercise, I think, yeah.
So when you take the derivative in that case for the quark Lagrangian,
Yeah.
I would have naively expected it's a vacuum to vacuum.
You would expect it?
Vacuum to vacuum correlation.
No, you're right. So here, yeah, here I've been a bit sloppy. So yeah, this would be on the vacuum. So I put the pion, okay? The point that, I mean, the vacuum, the difference between the vacuum and the pion, so basically I can consider the pion still a part of the vacuum, okay? It's indeed is a zero, is a massless excitation, so I can put this. Okay? Otherwise I have to do things a bit more complicated with the full reduction formula, but I think it's yeah, you can, if you want, this way you get differentiated with respect to the source, so you get specific green function, okay? Then you want to evaluate the green function of the same external state. So that is what I'm doing here. I'm putting the same external state in the two cases, but which in this case is also close to the vacuum. Yeah. Contains it, yes. Yeah, for the moment I didn't put any G Fermi, okay? Which is, so for the moment these for me are external field. So this doesn't need to be, you see, it doesn't need to be G Fermi. So this is a generic, so it's something, if I do two derivatives with respect to L, I can tell with L, so then I get the expectation value of a 4 quark billion of a product of two current at two different. So it's something, it's an object which is, okay, then if I put it at the same point, it will be a 4 fermion operator. But it's a specific 4 fermion operator, which then I think, you see, it's a, I start to do something tricky because it's not, again, yeah, will be a specific issue, but it's not the most general. Then for a 4 fermion, I can add an extra spurion directly coupled to the 4 fermion operator. So we end up to the situation where this will be an expectation value, but I cannot argue that this is the only contribution to a matrix element of a fermion operator. That is the point. And we will get back when we do weak interaction, okay? Because then for 4 fermion operator, I need to put the most general external. So 4 fermion operator cannot only come from the product to current. That is the thing. Well, later on, next lecture, we'll discuss the case of the photon, which for the photon, we want to make it dynamical at some point. But then we need to change theory because you see, because then you really need to put in your theory also to have, so again, it's a very big conceptual difference in treating the photon as dynamical field, because then I have to put it in the part here on which I have to do my integration. So if I just try to do some computings with the photon and then photon loops, I get new divergences because I've not really taken this dynamical in my functional integral. So I have to really make a different theory, again, which can be done, and I can do it along this line. But at this stage, with only this external field, I can only compute indeed something where I have my QCD that interact at some point with this external field. This external field, forget about QCD. Do whatever, decay to leptons, but cannot go back to interact with QCD. Otherwise, I don't have the tool to compute it. So I can compute a radiative decays, emission of photons, no problem. But photon correction, I mean, visual photon, no. Yeah, no, emission of photons. So here my pions are charged, and therefore here from that, I from this covariant derivative, you see, from this covariant derivative, now I can set in this limit, I get the coupling to the photon, okay? So for instance, I can compute process where, okay, my pion, then this, for instance, can do whatever you want. Or for instance, I can compute pi to pi gamma, where I even consider emission of the photon from external leg. However, okay, I can do this only at order, okay, E, what at the amplitude level, not more. So what I cannot include, okay, is this type of correction, because I don't have a way to handle these singularities. But for instance, radiative decays, I can do it if I'm interested really on a real photon, which I mentioned. So I don't have if I have a real photon, I don't have an infrared singularity, so I don't care about this. I can ignore it if the photon is really sufficiently high energy. Sorry, going back to a bit of physics. I feel a bit worried when all these formalism, but okay, I thought it was good to see a complementary view, and I also like the physics discussion. So just, but the formalism is powerful. That's